Hello, everyone. Today we're going to finish our discussion of electrochemical cells. Until now, we've talked almost entirely about galvanic cells. You may remember at the beginning that we said a galvanic cell is one in which the overall redox reaction is going in the spontaneous direction. In other words, the two half reactions would combine to go in the spontaneous direction for the overall reaction. Today we're going to talk about electrolytic cells. Now, I mentioned those briefly at the beginning, but electrolytic cells involve the same kinds of chemical reactions, except that by virtue of an external power source, they're forced to go in the non-spontaneous direction. And there are some things for which the non-spontaneous direction is the desired direction, as we'll see. Now, the overall behavior of either galvanic or electrolytic cells is determined by what are referred to as Faraday's laws, first developed and written down by Michael Faraday, of course. And during the discharge of either a galvanic or an electrolytic cell, the amounts of reactants consumed and products formed are governed by these so-called Faraday's laws. And they're very simple, intuitive, in fact, when you think about it. The first one says that the mass or moles of a given substance that's produced or consumed at an electrode is proportional to the quantity of electric charge that passes through the cell. In other words, the number of moles of electrons. We essentially talked about that when we were considering some of these galvanic cells and talked about the anode reaction releasing electrons that pass through an external circuit perhaps and into the cathode compartment of the electrolytic cell and cause something else to be reduced. The total amount of material that's oxidized and reduced is determined by how many moles of electrons pass through that external circuit. The second law, which is basically just another statement of the first one, is that equivalent masses or moles of different substances are produced or consumed at an electrode by passage of a given quantity of electric charge through the cell. In other words, the more coulombs of charge that pass through the cell, the more of the material being oxidized at the anode and the material being reduced at the cathode are reactive. Now, your book uses the capital Q, or script Q, to represent total charge. If the total charge on one electron, of course, is 1.6 times 10 to the minus 19th coulombs per electron, and there's an Avogadro's number of them, in other words, 1 mole of electrons, the total charge is the Faraday's constant, as we talked about before. It's 96,485 coulombs per mole of electrons. That may seem like a lot, but it depends on what the nature of the reaction is and how many moles of electrons are transferred and so on. We'll see some examples of that in a few minutes. So overall then, the current, remember, if you maybe remember from your physics courses, current is essentially the charge per unit time that passes a given point. The current in amperes is the number of coulombs per second that occur. And if that number of coulombs is represented by Q, the total charge, and the time is given by T, we just rearrange this, put the T over on the left side here. You can see that the current times the time that it flows divided by Faraday's constant is the number of moles of electrons then that pass through a cell. So if we simply measure the current and measure the time that it flows, we can determine how many moles of electrons have passed, and therefore how many moles of reactants and products were consumed or produced. Now, here's an example, a very simple one, of an electrolytic cell. This is simply the electrolysis of water, as it's called. Water, of course, is H2O, and the two reactions that occur at the anode and the cathode are written right here. At the anode, the reaction involves the oxidation of hydrogen from the water, from an oxidation number of, the oxidation of oxygen in the water from an oxidation number of -2 to an oxidation number of 0. It produces oxygen gas. At the cathode, the reaction is the reduction of hydrogen that's in water from +1 to 0. So hydrogen gas is generated at the cathode. The two reactions together are basically what is involved in water being converted into its elements, hydrogen and oxygen, both of which are gases. And so when this anode reaction occurs, that's listed right here, oxygen is generated, and visually you'll see it bubbling off the anode, whatever it's made of, coming off as bubbles of oxygen gas. On the cathode, you'll see bubbles of hydrogen coming off. And this is just a visual observation of the products of these two reactions. Of course, you can't see the H plus that's produced at the anode, and you can't see the hydroxide that's produced, but they're in the water. And so the combination of 4 H pluses that are produced at the anode and 2 hydroxides that are produced at the cathode essentially represents 2 moles of water. So the overall process is simply the conversion of water into oxygen and hydrogen, twice as many moles of hydrogen as moles of oxygen. Now, in this case, you can see that both the anode and the cathode, which can be made of any conducting but non-reactive material, platinum is common, rods of graphite are another example of something that's conductive but not reactive. All they serve is to conduct electrons either from or to one of the reactions that we just listed up here. Now, water, pure water, is not a good conductor, as you probably know. And so as a result, the conduction of electrons from the anode to the cathode would occur practically not at all, or at such a slow rate as to be immeasurable. So what's done is to simply put some salt in the water to make it conducting. In this case, sodium sulfate is used. And the reason that something like this is selected is because the sodium ion is essentially irreducible under ordinary conditions, and so it's a spectator ion, and so is the sulfate. Okay? And so all that happens here, if you think about it, is that it creates its own little internal salt bridge. It allows electric charge to be transferred between the anode and the cathode and maintain charge balance. So at no time is the charge imbalanced because it's all in the same vessel. Now, what's happening thermodynamically in a cell like this is that what we're trying to do is to cause what is referred to here as a driven reaction. That's the electrolysis of water, which is not spontaneous, of course. The reaction that's driven has a delta G that's greater than 0, of course, because it is non-spontaneous after all. And by itself, of course, it will not occur. It can be made to occur by something that drives it using a spontaneous reaction. Well, that's the reaction that occurs in the battery. The battery is essentially providing a source of energy to drive the reaction that's not spontaneous. And so long as the delta G, which is less than 0, of course, for the spontaneous reaction, so long as its numerical magnitude is greater than the reaction you're trying to drive, this reaction will occur. The extra energy that's used here is reflected usually in the form of heat. If you run a reaction like this and let it run for a while, you'll find that both the battery and the wires connecting it are getting warm. And that's the electrical work that's being done. So now, let's consider some examples of applied electrolysis that I just referred to them here as applications of electrochemistry. In particular, the production of some useful products. By useful, I mean ones that are produced in industry in large volumes. The first of these is the production of chlorine gas, Cl2. It's called the chlor-alkali process because, as we'll see in a minute, what's produced during the reaction not only is chlorine, but also sodium hydroxide. And we'll see how that happens in a minute. It turns out that for this overall reaction, 2 waters plus 2 chlorides, and it's the chlorides that are getting oxidized from -1 to 0. And of course, the conversion of water to H2 is causing the hydrogen to be reduced from +1 to 0, as we just saw in the previous slide. So the overall reaction then consists of these 2 half reactions, right? One is one that occurs as an oxidation and one that occurs as a reduction. Now, just to avoid any confusion with the terminology and the convention that we talked about earlier, you'll notice that these 2 reactions are not both written as reductions and then subtract one from the other. They're both written in the direction that they actually occurred during this electrolysis. The chloride in the solution, which comes from sodium chloride dissolved in the solution, by the way, as we'll see, the chloride is being oxidized to chlorine and producing 2 electrons for every chlorine molecule that's formed. The potential, the standard potential for that reaction is minus 1.36 volt, because if you look for this reaction in a table that we've looked at before, it will be written as a reduction, which is chlorine going to chloride, for which you would see that the E0 is plus 1.36 volt. So, but in this case, we're writing it already as the oxidation, so it's minus 1.36 volt. The other reaction, which is the reduction of hydrogen in water from plus 1 to 0, is written as a reduction, and its potential, which you can look up in a table, is minus 0.83 volt. And so in this case, we're adding these two reactions, not subtracting them when they're both written as reductions, because they're not. The first one is written as an oxidation. So adding these two reactions gives us the net overall reaction, which has an E0 of minus 2.19 volt. Now, that may seem like a small amount, but thermodynamically speaking, it's huge. It would correspond to an equilibrium constant of something like 10 to the minus 70th. So it's very unfavorable. Knowing the E0, you can determine what the delta G should be, or looking up delta G's of formation, you could do the same thing. It's plus 422 kilojoules, which is a lot. Again, that corresponds to an equilibrium constant of something like 10 to the minus 70th. So how does this reaction be carried out? Well, here's an arrangement that does it. You'll see it looks remarkably like the water electrolysis arrangement that we had here. And in fact, one of the reactions is exactly the same. This reduction of water, the hydrogen in water, to give hydrogen gas. That's exactly the same as the reaction, the cathode reaction that we looked at in the electrolysis of water. In this case, though, the anode reaction involves chloride being oxidized to chlorine and producing 2 electrons. Now, the solution itself, where does the chloride come from? Well, it's a solution of sodium chloride. Not only does that make the solution conductive, which it has to be, but it also provides one of the necessary reactants, which is chloride. So in this case, what occurs is that chloride gets reduced to chlorine, giving up 2 electrons. And here's the bubbles of chlorine gas that you can see coming off. And at the cathode, it's the same reaction as we saw for just the electrolysis of water itself. Hydrogen in water is going from an oxidation state of plus 1 to 0 and producing hydroxide. So what's occurring now is that hydrogen gas is bubbling off again, just like it did in the electrolysis of plain water, and hydroxides are produced, just like we saw in the electrolysis of plain water. But what's occurring in this case is we're getting 2 useful products. We're getting chlorine, and chlorine, elemental chlorine gas, is very difficult to produce because it would much prefer energetically to be reduced to chloride. And so as a result, it takes some reaction that drives it uphill in order to produce chlorine molecules. And what does that is the battery again. The battery has to be something that is either a variable voltage or a fixed voltage. Usually it's a variable voltage that can be adjusted to give the voltage necessary to cause this reaction to occur. Now, during the course of this reaction then, what builds up is chlorine gas, which in this case is not being usefully captured, but in industry, it's not this simple arrangement, of course, and so the chlorine that's produced is actually captured. And so is the sodium hydroxide. It's referred to, as I said, as the chlor-alkali process, and it's a very important process in industry for producing both chlorine and sodium hydroxide. Sodium hydroxide is also not easily produced by other means. And so the occurrence of this reaction requires some driving force to make it occur. Now, another way of doing this, if you think about it, is instead of having a solution of sodium chloride, what if we simply take a salt, sodium chloride, and melt it? In that case, there is no water involved. The only ions that are present then when the sodium chloride melts, and it's shown here as this green region, the only ions that are produced that are in this mixture, this melt, are sodium ions and chloride ions. So there is no water to be involved, which means you can't produce either oxygen or hydrogen, but only the reactants that are available. In this case, the reaction that occurs, again, is, as in the previous case with the sodium chloride solution, is just chloride going to chlorine. Chloride ions in the melt are interacting with the anode that dips into here, which again could be something that's conductive but non-reactive, like platinum or graphite. It produces bubbles of chlorine gas again, which again in industry wouldn't be just bubbled off, they would be captured in some closed system. And two electrons. The two electrons, again, go through the external circuit, but now, instead of reducing hydrogen from the water from +1 to 0, there is no hydrogen because there is no water. So the only thing that's in there that can be reduced is sodium, sodium +1 ions. And so the reaction that occurs at the cathode is very simple. It's just sodium ions reacting with those two electrons that have come over from the anode to produce two atoms of sodium itself. Well, the sodium, because of the temperature involved here, because the sodium chloride is molten, the sodium metal is less dense than the sodium chloride melt. And so as a result, it floats on the top. That's what this blue region is here, liquid sodium metal. And the overall process then produces two useful products, chlorine gas and sodium metal, which is impossible to produce by any means other than electrolytically, because sodium metal is so difficult to reduce, or sodium ions are so difficult to reduce to sodium atoms. So that's one example of the application of electrolysis to making useful products. Another one is the process by which aluminum metal is made. Extremely important process in industry, as you probably know. Aluminum is second only to iron in the amount of it that's produced in our economy, in fact, in the entire world's economy. It's produced by what's called the Hall-Héroult process, and it involves some very difficult reactions that can be carried out only electrolytically. If you consider the reduction of aluminum ions from +3 to 0, it's this simple step right here. Aluminum 3 going +3 electrons going to aluminum metal. Well, where does the aluminum 3 come from? Well, the standard way of doing this in industry is to use aluminum oxide, which as an ore is referred to as bauxite. It's the commonest ore of aluminum oxide. And so it provides the source of aluminum. However, in comparing it to the molten sodium chloride we just talked about, which can be electrolyzed, sodium chloride melts at only about 500 degrees C, and so it's not that difficult to make a melt of sodium chloride. But aluminum oxide melts at more than 2,000 degrees Celsius, which means that it consumes a huge amount of energy to melt it, and for that reason, it's not practical. However, it happens that it dissolves in another molten salt, which is sodium aluminum fluoride, Na3AlF6, which is referred to as, its common name is cryolite. And cryolite melts at still a high temperature, but less than 1,000 degrees. That makes it low enough to be practical, that it doesn't consume more energy than you produce. And so aluminum oxide, the bauxite, can be dissolved in sodium aluminum fluoride as a molten material. And now, just like with the sodium and chlorine production that we just looked at, it can be used to produce aluminum metal. And unfortunately, the side product is something we'd rather not have, but there simply is no other way to carry out this process. The cathode reaction is aluminum 3 +3 electrons going to aluminum. The E0 for that reaction is -1.66 volts, quite high, in fact. The delta G that corresponds to that, which you remember we can calculate by delta G equals -NFE, the delta G is +2,000 kilojoules. So you can imagine that the equilibrium constant for this is extremely high, and it can only be carried out by forcing it to do that by some external source of energy. So this is the cathode reaction. That's the reduction. The anode reaction is this. It's the two oxides from the aluminum oxide, two oxides in the melt will react with the graphite anode itself. This is an unusual process in which the anode itself, which are graphite rods, great big graphite rods, the anode itself is sacrificed during the course of the reaction. So the anodes gradually, over a period of time, are eroded away and have to be replaced. And it turns out that in order to keep something from reacting further, you have to have something that's virtually chemically inert, like graphite, at such a high temperature of 950 degrees C. And so, unfortunately, the product that forms when oxides react with the carbon is CO2, +4 electrons. Carbon dioxide, of course, has to be captured. It's something that you should not be released into the atmosphere because it's a potent greenhouse gas, as you know. And so the aluminum smelting industry, as it's called, has to capture as much of the sodium as carbon dioxide as possible because it simply can't be released. The overall reaction then is this. This is the balanced reaction: 4 aluminum 3s in the melt, plus 6 oxides also in the melt, that's from the molten aluminum oxide, plus 3 carbons from the graphite anode, reacting to form 4 aluminum metal atoms and 3 CO2 gas molecules. So as you can see, you produce almost as many moles of CO2 as you do of aluminum, 3/4 as many moles. Unfortunately, there is no other good way to do this. There's no other anodic process that can carry this out and enable the oxide to become the oxide to be combined with something else. In this case, the carbon, as you can see, is being oxidized. It's going from 0, which is what it is in elemental carbon, to +4. That's why the 4 electrons show up here. Okay, and so the oxygen stays as -2, which it almost always does anyway. So what's shown here then is, here is the aluminum oxide in the melt right there, and this is the anode, the carbon, the graphite, and the aluminum that forms is molten because of the high temperature. Aluminum melts at lower than 950 degrees, and so the aluminum that forms during this process will come out as a liquid. It doesn't come out as a solid. So how is that carried out? Well, it's a very rigorous process. Here's a simple schematic. They don't exactly look like this. They don't have little burners under here. They don't have buckets to collect the aluminum. But the overall chemistry is essentially that. Here are those large graphite anodes, and there's usually a whole bunch of them. They're all connected in parallel. This is the steel conductor here that carries the current that you're providing from this external battery source. And in here is this light yellow material. That's the molten sodium aluminum fluoride, the molten cryolite, in which aluminum oxide is dissolved. So it actually looks, it's not quite a clear liquid, but it's not something that looks like a solid at all. So during the course of the reaction then, as we've just seen, what happens is the aluminum in the melt, that's part of the aluminum oxide that's dissolved, picks up 3 electrons from the anodic process and produces aluminum. That aluminum, turns out, is more dense than the aluminum oxide cryolite solution here. So it sinks to the bottom as liquid aluminum right here. Now, in industry, there's a more sophisticated way of getting the aluminum out. It doesn't get drained into a bucket, but the principle is the same. The aluminum is drained out and periodically as the reaction proceeds. Otherwise, it would build up to larger quantities. So as this happens, more aluminum oxide and cryolite are added to keep it melted. It doesn't work by using burners to melt this, by the way. It uses a source of electricity. And so the electricity that's applied to the electrolysis process is applied across these 2 steel conductors, the cathode here and the anode here. And the reason that this is referred to here as a frozen electrolyte crust is because this stuff is one salt dissolved in another salt, right, which occurs at, if the temperature is high enough, at just about 1,000 degrees. But because if it's exposed to anything lower than that, which means entire surrounding atmosphere, it will solidify and form a crust on top. And in fact, that crust helps to insulate it and keep it liquid inside. So it serves 2 purposes. So this is the overall process by which aluminum is manufactured in industry. In fact, there simply is no other way to do it. The only way to form aluminum metal, which is the second most important metal in our economy, the only way to form aluminum metal is to reduce some source of aluminum 3. Now, you might say, well, why use aluminum oxide, which has this very high melting point that requires this cryolite to dissolve it? Why not just use aluminum chloride, which melts much lower, just like sodium chloride does? Sodium chloride can be melted like this. Aluminum chloride can do the same thing. You say, well, why don't we just use aluminum chloride then? Save a lot of energy from heating up all of that bauxite in cryolite solution? Well, the answer is what we just talked about before. In the overall process, if we used aluminum chloride as a melt, yes, the aluminum would be formed at the cathode. Aluminum free would be going to aluminum metal. And the aluminum in that case is more dense than the solution itself, so it would sink to the bottom, as we just saw. But what would be produced at the anode? Well, at the anode, what would happen is exactly what you see here. Chloride, from the aluminum chloride melt, it's the chloride that would get oxidized. It would get oxidized from chloride to chlorine and produce chlorine. So what we would be producing in this process, if we carried it out this way, is chlorine gas, which we don't want. And the reason for that is because chlorine, or the chloride and chlorine coupled, has a lower potential than the oxygen one does. Excuse me, back here. So that this reaction here of oxide reacting with carbon to form CO2 would not occur, simply because it's easier to oxidize chloride than it is to oxidize the oxide in the carbon, or with the carbon, and the carbon rods. So that's the reason why it requires some mixture in which the only thing that can become oxidized is the oxygen that occurs in the aluminum oxide by reacting to form the oxygen gas that we talked about. It will form, I keep covering this thing up, it will form CO2 by reacting with these graphite anodes. You can't just do it with an aluminum chloride melt, or you would be producing chlorine, excuse me. Now, let's look at a couple of other things that involve these electrochemical reactions. You've all seen what are called dry cells, flashlight batteries as they're commonly referred to. This is a very old technology. It dates at least 100 years ago or more. They're still used to some extent, but not with the original chemistry that the original ones used. And so the structure of these things makes use of the reaction in what's called a conventional Leclanché dry cell. It's called a dry cell, even though it's not technically dry. This material in here, as we'll see in a minute, is a paste. That's kind of a moist paste. It's not really dry, but because it's enclosed in an entire metal container, it's a lot easier to deal with than something that involves a liquid like this, which is useful in the laboratory, but from a practical standpoint, as a portable source of electricity, it's not very practical. And so that's the reason why the so-called dry cells were developed over 100 years ago. The reaction that's involved is zinc metal, which forms, you can see the label here, it forms the casing itself, the can, as it's called, that surrounds the inside. The zinc anode is formed by that entire casing. The zinc itself gets oxidized to zinc 2, which is conventional oxidation of zinc. And in fact, that's a very favorable reaction. That's a downhill reaction. Zinc, in going from zinc to zinc 2, it releases energy. It's a delta G less than zero reaction. The anodic reaction, the cathodic reaction where something gets produced, is manganese dioxide. Manganese dioxide exists in a few different forms, but mostly it's a black powder. And it's the manganese in manganese dioxide is +4, as you can see, because the two oxygens are both -2. And so the manganese goes from +4 to +3. It gets reduced to manganese sesquioxide, as it's called, Mn2O3. The thing that conducts the electricity in and out is ammonium chloride. So the ammonium ions here essentially are what result in conducting the current through there. The ammonium chloride and the zinc chloride that forms from the oxidation of zinc. When the zinc goes from zinc to zinc 2, there has to be an anion that goes with it. And so the electrons that are released in that reaction reduce the manganese from 4 to 3. And so the ammonium chloride is in there as essentially something to make this conductive. because it's not really dry. It's kind of a moist paste. That's what allows electrons to be transferred in and out of here as the reaction goes. And so the overall reaction process, you can look these up. The zinc to zinc 2 couple is, you can look up the half cell potential for that. You can also look up the manganese MnO2 Mn2O3 couple, and you'll see that when you combine those, it leads to an E0 of 1.5 volt, a voltage that you're probably used to if you use dry cells for things, or flashlight batteries, or whatever. And so the reason that this occurs the way it does, the ammonium ions are simply spectator ions. They do nothing except to provide for to make this a conducting material in here. Okay, and so the overall operation is what you see here, these reactions. Now, these conventional, the old-fashioned dry cells aren't really used much anymore. Nowadays, most of them use what's called an alkaline dry cell, in which the ammonium chloride that was in here is replaced by potassium hydroxide, and the KOH serves as a means of making this a conducting material. In this case, the same reaction occurs with zinc going to zinc 2, in this case zinc 2 hydroxide, but now it's combined as zinc hydroxide, which is not soluble. It stays in that paste. It doesn't form a zinc 2 chloride as it would up in this cell. And so the zinc gets oxidized to zinc 2 in the form of this zinc hydroxide. Again, the MnO2 the manganese gets reduced to manganese 3, forming this stuff. And so the overall cell, though, since it involves the same half reaction of zinc to zinc 2 and manganese dioxide to Mn2O3, it yields the same cell potential because it involves the same 2 half reactions. It's just that ammonium chloride has been replaced by KOH as the conducting medium. But these are both examples of what are called dry cells. And most of the time now, if you look for flashlight batteries or something, you'll find that they're always shown as alkaline batteries, alkaline dry cells. Another example of a cell like this, that you probably have seen, are these so-called button batteries that are used in watches and calculators and various other things. And they're useful because they can be made in a very low profile geometry. They obviously, because of their small size, they don't have as much total amperage available. Remember that what we talked about previously when we said that the cell potential is an intensive property. What that means is it doesn't depend on the size of the cell, so that a D cell, a C cell, a AA cell, or a AAA cell all have the same voltage, even though they have very different sizes. And that's because the cell potential is an intensive property. So the chemistry that's involved in these cells, again, involves zinc. The zinc is going from zinc metal to zinc hydroxide, which is an oxidation from zinc 0 to zinc 2. But now the cathode reaction involves mercury oxide, HGO, going from mercury plus 2 to mercury 0. It produces mercury metal. Now, the cell potential for this overall process is 1.34 volt. It's similar, a little bit lower than the standard zinc manganese dry cells, but it's one in which the cell potential can be used for many of the same things on a smaller scale, because these things are typically on the order of only about 1 centimeter in diameter and half a centimeter high. But the reason that they're useful is because they are so small and portable. So the anode in this case is a mixture of mercury and zinc. Mercury metal and zinc metal form what is the anode, because they're both conductors, of course. The cathode is the steel casing. That's this outer steel case. The cathode is the steel casing in contact with solid mercury oxide, which is inside. And the electrolyte stuff that's packed in here is the moist KOH solution. 45% KOH is almost not a liquid. It's almost more like a slush or a gel because it's so thick. And that's the intention. You may have heard or read that these kinds of cells are not supposed to be thrown into the trash and certainly not incinerated. The reason for that is because they produce metallic mercury, which is toxic. And so for that reason, these kinds of cells have to be disposed of in a proper manner rather than being thrown into the trash or incinerated, because the mercury would then escape into the atmosphere, which is undesirable. Now, both of those, all of those cells that we just talked about, the Leclanché cell, which is not used so much anymore, but the alkaline dry cell and the mercury zinc dry cell are one-way batteries. What that means is that when they discharge, here's the alkaline one, when they discharge, they form something that is not easily reversed to recharge the battery. The zinc hydroxide is not, and the manganese 3 oxide is not. They both are essentially final products that it's very, very difficult to try to reverse them and make it go back to zinc and MnO2. The same thing is true for the other dry cells like this. And it's for that reason that these are referred to as simply discharge batteries. But there's an important usefulness, of course, for batteries that are rechargeable. And these are ones in which the reactions, the anodic and cathodic reactions, can be forced to go back and be recharged again by an external source of energy. One of the most long-standing ones of these that you undoubtedly heard of is the lead acid, as it's called, rechargeable battery. And this is a very old technology. It was developed more than 100 years ago, around the turn of the 20th century. And the chemistry involved is fairly simple, but very, very interesting. It's very unique because the cell itself consists of lead in three different oxidation states, actually, 0, 2, and 4. And the overall chemistry involved is very straightforward. Lead as the anode, lead metal serves as the anode. That's why these batteries are so heavy. Lead serves as an anode, and it's in contact with a sulfuric acid solution inside. Well, older batteries were like that, and that's why the sulfuric acid would have to be replenished from time to time, and it would slosh around. It was dangerous, in fact, if you were in a car wreck, because it would spill all over the place. Now, most modern batteries use what's called a MAT arrangement, AGM MAT arrangement, in which there is not liquid sulfuric acid used anymore. It's all contained on these spongy mats, so it can't spill. But the chemistry is still the same. The lead anode, all right, it gets oxidized to lead sulfate, which is lead plus 2. All right? That's the sulfuric acid in there that's providing the source of the sulfate. The sulfate is essentially a spectator ion. It takes a sufficiently high voltage to cause it to do anything that it doesn't. And so the sulfate just remains as a spectator ion. And as you know, when sulfuric acid ionizes in water as a strong acid, it produces hydrogen sulfate ions. And so that's what's in the liquid container. I'll talk about the old-fashioned ones. That's what's in here that's present as what starts out as sulfuric acid, because sulfuric acid in water will completely ionize to give HSO4-. Removing the second electron, as we know, the second proton, that's a weak acid, and so it doesn't occur to a very large extent. And so what's produced then, because of the sulfuric acid in water, is hydrogen sulfate and hydronium ions. This is what started out originally as sulfuric acid, but this is the way it's maintained in the battery. And so the lead dioxide is essentially coated on the lead, on the lead electrode. And so what happens during discharge is lead metal gets oxidized to lead 2, which now becomes lead sulfate, which is also a kind of whitish material. And the other electrode, which consists of lead with a coating of lead dioxide, the lead dioxide, of course, the lead is plus 4, because there's 2 oxygens and they're minus 2. The lead 4 gets reduced to lead 2. So both the oxidation at the anode and the reduction at the cathode form the same product. It forms lead sulfate. That's why the chemistry involved is kind of unique, and why it's been used for so many years, because it's all self-contained. Now, in the overall reaction process then, the reaction itself, if you put the 2 half reactions together, is lead plus lead dioxide, it's lead 0 and lead 4, plus 2 molecules, essentially of sulfuric acid, if you will, form 2 moles of lead sulfate, which is a solid, it's not soluble in the sulfuric acid solution, and 3 waters. The cell potential for that cell is just about 2 volts, actually a little bit higher. Now, these individual cells, and if you look here, modern batteries are 12 volt, as you know. They consist of 6 cells like this that are all arranged in series, back to back. And so the total cell potential then is the sum of all of these 6 individual ones, which is 6 times 2 or 12 volts. Actually, when a 12 volt battery is completely charged, the potential is something like 13.2 volts, because the cell potentials here are actually slightly higher than 2 volts, but they're usually referred to as 12 volt batteries. Now, here is the cell notation for that cell. And at first it may appear confusing because the convention, of course, is that the anode is on the left, the cathode is on the right, so the reaction flows from left to right. And you might say, well, wait a minute, this is lead over here. You're showing lead on both sides. How can this be both the anode and the cathode? Well, this is the anode, the cathode over here, even though it may not look like it, because what's happening is that it's not the lead that's getting reduced, it's the lead dioxide, which is plated or coated onto the lead itself. And that's why the overall reaction involves lead dioxide, but lead dioxide, you cannot make an electrode out of it. It's just a red oxide powder. And so it has to be coated on something. And what it's coated on is lead itself. So the lead forms both the anode, which is lead metal being oxidized, and it forms the cathode carrier. It essentially is carrying the lead dioxide. So in between, both of these wind up going to lead sulfate. And so it does indeed proceed from left to right. Lead metal is going to lead 2 sulfate, all right? And here's the surface of the electrode. And lead sulfate is being formed from the lead dioxide being reduced to lead sulfate. And so the same product is formed, and that's what makes this chemistry unique. The same product is formed from both the reduction reaction and the oxidation reaction. They both form lead sulfate. And so here's the overall chemistry. Now, of course, as you may know, the main usefulness of a battery in a vehicle is to start the engine. The internal combustion engine is essentially involves the chemistry of the fuel burning and so on. But to get it started, to get the engine turned over and started, requires a real kick in the pants. And that comes from the battery. Battery essentially serves as the source of energy to start the car. If you turn the ignition key in your car, it starts a starter motor. It's a DC motor, which is inside the engine compartment. The battery is powering that DC motor, and it's connected by belts to the crankshaft of the engine, and it gets it started. If the battery's in good shape, it will usually take only a couple of turns and the engine is started. And so at that point, the battery's not used anymore for running the car. But because of the large amount of current that's required to start the engine, if the battery remained in that state, within about 6 or 7 starts, it would become too low a voltage to be useful. It wouldn't turn the engine over anymore. So there has to be a way for the battery to be recharged, which is what makes it useful and has been for many years. There has to be a way to recharge the battery. Well, that's the function that's served by the alternator in your car. Once the engine is running, the alternator is also connected by a belt to the crankshaft. And an alternator is essentially just a dynamo. It's turning something that generates electricity. And what it does is to provide electricity to cause this reaction to go in the reverse direction from what we're talking about. So if the battery is used efficiently and it starts the engine and it's not weakening itself, then it doesn't take very much electricity to recharge the battery and get it back to its original state. And it's for that reason that there has to be something called a voltage regulator that's in series there, so the battery cannot overcharge, and that would start to corrode away all the lead. So, but the overall system is a very unique one that has proved its worth by still being in use more than 100 years later. There are better ways to do it now, of course, but the vast majority of vehicles still use lead acid storage batteries. Of course, electric vehicles don't do that. I'm not going to talk about those in any detail, but the technology involved in the so-called lead-acid storage battery is a very important one that continues to be used in the vast majority of vehicles that are on the road. So that's one of the rechargeable batteries. Another example is a much smaller one. It's called the nickel cadmium or NiCad battery. And it involves this chemistry. Cadmium, solid, gets oxidized from 0 to +2. Cadmium hydroxide is Cd +2. And nickel gets reduced from nickel 3 to nickel 2. You'll notice the stoichiometry here of nickel oxyhydroxide, as it's called. The oxide, of course, has a charge of -2, or an oxidation number of -2. The hydroxide is another -1. So the nickel is +3. And it's getting reduced from nickel 3 to nickel 2, which is what the nickel hydroxide is. And the chemistry that's involved here is such that it can be reversed by providing a power source. The cell potential here is about 1.34 volt, same as what we saw for that battery up here, okay? Because some of the chemistry involved is the same. And so the difference is that the nickel cadmium battery can be reversed because it is possible to reduce cadmium 2 to cadmium. It doesn't take that large power to do it. And nickel 2 can be oxidized to nickel 3 again. And so these are the kinds of batteries that can be recharged with a charger in the wall until lithium ion batteries came along 10 or 15 years ago. This was the commonest kind of battery that was used even in portable computers and other portable devices. They exist in the form of batteries, what we would call a battery, but it's a cell that looks like a double A size or a triple A size battery, but it's not the usual chemistry. It involves nickel cadmium. And these have rechargers that can charge the battery back again, and they will last for several hundred cycles before the cadmium and the nickel no longer completely recharge or discharge and recharge in the same way. And so eventually they can't be recharged anymore, but it takes several hundred charges for that to happen. So it's a very useful type of battery. So finally, we'll say something about a battery that's all of you are familiar with, that serves a very important purpose nowadays. That's the so-called lithium-ion battery. It's what powers your cell phones. It's what powers your laptop computers. And in a larger scale, it's what powers electric cars now, like the Tesla and some others that have been produced in recent years. The reason that the lithium-ion battery is so useful for devices like this is because of the simple fact that it uses lithium, which is very, very light. The density of lithium is sufficiently small that batteries with the same amperage possibility that are made from other metals weigh 2 or 3 times as much. And so they're not as practical as the lithium-ion battery is. Certainly not for vehicles where there's a large number of these lithium-ion batteries that are contained in an electric vehicle, and they simply cannot be too heavy, or it will take half of the power that the battery provides just to carry along the weight of the battery. So that's the reason why they become so important in recent years. I'm sure you've read about them. Now, in the lithium-ion batteries, it's another example of some very interesting chemistry. Both the anode and the cathode are materials into which and out of which lithium ions can migrate. The reason that happens is because lithium ions, of course, as you might know, because lithium atoms are small, lithium ions are even smaller. So they can easily migrate in and out of the cathode material and the anode materials that make up the battery. Now, during insertion, as it's called, or intercalation, lithium ions move into the electrode. And during the reverse process, which is the extraction or deintercalation, lithium ions move back out. And so the ease with which they can do that is what makes this particular combination, this type of battery, very, very useful. When a lithium-based cell is discharging, okay, same as we've seen for some other batteries, the lithium is extracted from the anode and inserted into the cathode. And when the cell is charging, the reverse occurs. So the cathode half reaction, with charging being the left to right mode and discharging being the right to left mode. The cathode half reaction then consists of lithium cobalt oxide. Cobalt is the other metal, and it's one of the limitations, in fact, that makes this so important on the world economy scale, because to make lithium-ion batteries also requires cobalt. And the US, for example, does not have any large deposits of cobalt, and we have to import most of it to make these batteries. We also don't have a lot of lithium deposits in the US, for that matter. And so both of these two metals that are in the lithium-ion battery are ones that have to be imported. And so they're subject to some important trade barriers sometimes that are not helpful. Anyway, in the cathode half reaction, with the charging being from left to right, lithium ions are +1, cobalt ions are +3. So what happens then, cobalt is +3, I'm sorry. In this case, some of the lithium migrates out of there. That's what these X lithium pluses are representing here. And what's left in the cathode is the cobalt and the oxygen are still there, but some of the lithium, a small amount, has migrated out. And because it's a plus charge, it also has to have electrons going with it. This is the source of electrons that make the battery power other things. The anode half reaction that occurs when this reaction is occurring at the cathode is just the opposite. X of these lithium ions plus some electrons are moving, plus some carbon, that's where it's embedded in graphite, forms this lithium sub X. And the reason it's just called X is because it's a variable stoichiometry. It's not a simple material like this that has a fixed stoichiometry of 1 lithium, 1 cobalt, 2 oxides. Instead, it depends on what this X is, and X could be different depending on different configurations. But the principle is still the same. The reason that this works is because lithium ions, which are so small, can insert themselves into graphite. Graphite, of course, is a layered-like material, as you know, and it can accommodate lithium ions in between, and the lithium ions become partially reduced, and as a result, forms this indeterminate material. And so during the discharge, during the charging process, this is what happens. During discharging, now the reactions go in the opposite direction. What occurs at this electrode is that lithium ions move back out again. They move through with their electrons. That's where the electrons come from, the power devices. The lithiums, and remember, this makes it look like they're two separate vessels, but they're not. This is all part of the same device right here. And so it's the electrons that are mobile, that go outside when they're produced by the anode process, go through an external circuit to do whatever it's supposed to do, and then they come back into the cathode. And so you have to look at this like, here's these electrons, and they wind up in being produced in this half reaction, going from right to left. And here they are coming into this half reaction, going from right to left also, and they reform lithium cobalt oxide. And so this is a very important type of battery, as you know. I'm sure you've all got one in your pocket right now from your cell phone, as well as your laptops. In laptops, they have to be made in certain geometries, of course, just as they do in phones. They have to be very thin, and for that reason, they have to be very low density. Because of the low density of lithium-ion batteries have the lowest attainable weight-to-power ratio of any commercial batteries, making them particularly useful for, as you know, mobile devices such as cell phones, cameras, and laptop computers. Lithium is, of course, the least dense of all metals, and lithium ions are very low density. And so as a result, batteries, one of the most important measurements of a battery is what's described here, the weight to power ratio. The smaller the weight is, or the larger the power, the better the battery is. In other words, the battery can be smaller and use less volume and less weight. One other thing I wanted to mention is another kind of, it's not really a reversible or a rechargeable battery, but it's a fuel cell. You've probably all heard about fuel cells. they're not the same thing as electrolytic cell in the usual sense. What they consist of are reactions that involve, and they can be made out of a number of different kinds of reactions. But what they essentially do is to react hydrogen and oxygen to produce water, steam. So the only product of a hydrogen-oxygen fuel cell is just water. There are no side products. There are nothing that has to be gotten rid of. And so the overall chemistry, though, is very simple. Hydrogen and oxygen are both fed in to, there are these porous, they refer to it as a porous carbon cathode and a porous carbon anode. It's something that keeps the solution contained, but the hydrogen and the oxygen can penetrate through it. And so what happens on the hydrogen side is that hydrogen is getting oxidized from 0 to +1 is what it is here. All right. And so the hydrogen reacts with the hydroxide that's in here. This is a hot potassium hydroxide electrolyte, typically on the order of several molar. So it's very corrosive, but it's easily contained, as a matter of fact. And so because it's porous, the hydrogen can penetrate through here, react with hydroxides to produce water and 2 electrons. On the other side, oxygen can also penetrate through here. It reacts with the oxygen reacts with the water and 2 electrons to produce hydroxide, which in turn gets back into the reaction with the hydrogen gas. So as a result, the process goes back and forth. Hydroxide ions are moving in this direction to react with hydrogen gas, and K pluses, which are, it's KOH over here, are reacting to over here to produce the hydroxide ions that are needed for oxygen to react with water. So the net result of the whole thing is that hydrogen and oxygen are combined into form nothing but water, and the KOH, in essence, even though the hydroxide does react, but it's reformed again. So it's not strictly speaking correct to call it a spectator ion, but in essence, the KOH remains constant in here. And of course, you may have already read that fuel cells, particularly hydrogen oxygen fuel cells like this, were the ones that were used and still are in spaceflight. And the reason is because they produce no byproducts, they produce nothing but water, and in fact, they produce the drinking water that the crew needs. You don't have to carry along water for drinking, which weighs a lot, and weight is a very important factor in spaceflight. And so the fuel cell is used to produce the water that they drink, but more importantly, or just as importantly, it produces power, okay? Because the voltage across here is the voltage that exists across essentially a hydrogen-oxygen electrolysis reaction we looked at before. It's essentially serving the same purpose, but in reverse. Now we're putting oxygen in and hydrogen in instead of producing them electrolytically and having them come out, as we looked at in that water electrolysis process. And so, as you may have heard about the so-called accident or incident on the Apollo 13 mission way back in 1972. This was the mission that had to get aborted. You may have read about this. And the reason it happened is because the oxygen and the hydrogen are stored in separate vessels, separate tanks, essentially pressurized tanks. And they're stored in a liquid form. So what happened when they had to periodically, as a regular routine, stir the oxygen tank is that there was a short. Some wire was not installed properly, and there was a short that caused the oxygen tank to blow out the side of their spacecraft. And it led to this odyssey that everybody knows about now, where they had to do what they could to move themselves into the lunar module that was intended to land on the moon, which never did, and use that as a kind of a lifeboat to get them back to Earth. But that came about because of the oxygen tank blowing out, one of the 3 oxygen tanks blowing out on what was supposed to feed the fuel cells. So this is there's a lot of work being done during the last 10 years or so to develop fuel cells like this for use in automobiles, because it would be the same way. It produces absolutely no pollution. It makes nothing but steam as the product of the the fuel cell discharge. Of course, it means you have to carry some hydrogen and oxygen around with you. The oxygen is not a problem, but the hydrogen is something that can be dangerous, obviously, if you have a large amount of compressed hydrogen on a vehicle. It has to be properly contained, and that's part of the technology that's being developed, is not have the hydrogen be a tank of compressed hydrogen, but rather have it contained in a solid that releases it as needed. And there are research that's being done to develop these hydrogen absorbing materials. And of course, they have to absorb hydrogen, but they also have to be sufficiently light that they're not adding too much to the weight of the vehicle. In any case, hydrogen oxygen fuel cells are an important technology that's developed for vehicles right now. So I hope we are now experts on our the technology involved in these various electrolytic and galvanic cells. So